We're going to start off our afternoon session with Dr. Hobgood's presentation. Dr. Hobgood is an associate professor of geography here, and he really likes to study hurricanes. So here he is.
Thanks, Josh. That's probably the most accurate description Josh has given of anybody. I do really like to study hurricanes, which means I'm trying to just survive till we get to June 1st and start a hurricane season. You folks can have this colder weather. All right. I follow all hurricanes really closely. And so what I'm going to show you today is a comparison of two of the more impactful hurricanes that have happened in the Atlantic in the last 2 years. Hurricane Michael in 2018 and Hurricane Dorian in 2019. And I'm going to try to convince you that even though they happened in different years, and different months, and different places, they're actually pretty much alike. All right. So, if you don't follow hurricanes, here's a little bit about Hurricane Michael. 2018, the time period I'm going to talk about is October 6th through 10th. It actually lasted longer than that, but this is the part that I'm interested in. It made a landfall near Mexico Beach, and Ryan, I guess, surveyed some of the damage after that. Maximum sustained wind was 160 miles per hour. 16 deaths according to the NHC Tropical Cyclone Report, $25 billion worth of damage in the U.S., and it was the fourth Category 5 hurricane to be known to have hit the U.S. coast. The other three, Camille, 1969 August storm, the Labor Day hurricane in 1935, obviously Labor Day, and Andrew, 1992 South Florida August storm. So in October, Category 5 hitting Northwest Florida is a little on the unusual side. Dorian was just last year. If you follow weather at all, you couldn't miss this. Time period I'm going to talk about too is the time period up until it affected Grand Bahama Island, so it's August 28th through September the 2nd. The two landfalls I'm going to talk about are the Abacos and Grand Bahama Island. Maximum sustained wind speed for Dorian was 185 miles per hour, and this was measured by aircraft, so it's not satellite derived or anything like that. NHC has not released its tropical cyclone report for Dorian yet. It'll come out later this spring sometime. Fatality, casualty estimates, as those of you who work in this area know, can be iffy, so there's an unknown number of deaths. And the death toll is substantial, but I like to consider myself a careful scientist, so I don't want to throw out some number out there I don't have a lot of faith in. Catastrophic damage on Grand Bahama Island, again, I don't have a figure to give you there. And at 185 miles per hour, it ranks as one of the most powerful hurricanes on the record for the Atlantic Basin. All right. So this map shows the tracks of the two storms. The yellow circles are when there were tropical depressions. Orange circles represent tropical storm. The red are hurricanes, the purple are major hurricane, and the black circles are when it's a Category 5 hurricane. And as you can see, October, where do you expect a hurricane to start? Northwest Caribbean Sea. It's exactly where Michael started. Moved northward, gradually intensified, became a hurricane in the southeastern Gulf of Mexico. Really typical. Moved up into the northern Gulf of Mexico, became a major hurricane, and it was a Cat 5, and it was intensifying as it hit the east coast, northwest Florida coast. Not typical. Most hurricanes, doesn't matter whether it's August, doesn't matter whether it's a Category 1 or Category 5 hurricane, weaken when they get close to the Gulf Coast. They either move into an area where there's more wind shear, there's dry air that gets sucked into the western side. That didn't happen with Michael. And in fact, I can only remember two major hurricanes that hit the North Gulf Coast while they were intensifying. Camille in 1969, which hit the Mississippi Gulf Coast as a Category 5, and Eloise, which hit Northwest Florida, ironically just a little to the west of Panama City. Right? Mexico Beach is a little to the southeast of Panama City, but in the same general vicinity as a major hurricane in 1975. Other than that, I mean, Katrina was a Cat 5 over the Gulf of Mexico. It was on the borderline Cat 2-3 by the time it got to the coast. It was weakening. So that's unusual. Right? Over here on the right, you can see Dorian, right? August. Dorian formed in what some people call the main development region east of the Caribbean Sea. Typical, strengthened into a tropical storm, moved through the Windward Islands. And again, I'm not going to talk about it. Dorian did cause flash flooding and fatalities in some of the Windward Islands, so I don't want to belittle that. Dorian almost fell apart after it moved through the Windward Islands, but a new center developed a little farther to the north. Dorian then moved east of Puerto Rico, became a hurricane north of Puerto Rico, became a major hurricane as it approached the Bahamas, and a Category 5 hurricane. Right. Most of these dots are 12 hours apart. I've removed a few of them in some places just to make the map easier to read. But those two black dots there on Grand Bahama Island, that's how far Dorian moved in 24 hours as a Category 5 hurricane. And that was part of the reason why there's such catastrophic damage on Grand Bahama Island. Right. Now, this is Hurricane Michael over the Gulf of Mexico. It was a major hurricane at this stage. It had not reached peak intensity. It didn't reach peak intensity until it got to the coast. Right? Whenever you see a hurricane like this, where you got circular clouds at the top, that means there's not much wind shear. The upper level divergence is going out in all directions. The odd thing here is normally in the Gulf of Mexico, the strongest, coldest cloud tops are on the eastern side. Here they're on the western side. And the western side is usually truncated. It's really usually a lot smaller than the eastern side because the dry air is coming around the western side. You can see that didn't happen with Michael. This is Hurricane Dorian, 185 miles an hour. You can see the eye there is right over the eastern end of Grand Bahama Island. Right? Same sort of circular shape, and the cloud tops actually aren't quite as cold as they were at Michael. Part of that is the atmosphere was warmer there. I mean, this is August near the Bahamas. All right. Now, one of the ways I compare hurricanes is that after Hurricane Sandy, I created my own hurricane index. The Saffir-Simpson scale, and some of you, I talked about this index the last time I talked at a symposium a few years ago, so some of you may have heard a little bit of this before. But the Saffir-Simpson scale doesn't take size into account. And when Sandy was approaching the U.S. coast, people kept asking me, well, how bad is it going to be? And I said, you've got to think of it, it's going to be like a large major hurricane. And the comment I got back more times than any I can care to remember is, but it's only a Category 1 hurricane. Yeah, but it's a real big category. And Sandy ended up doing $50 billion worth of damage, but it's only a Category 1 hurricane. So I decided to create my own hurricane scale. I'm just going to review it briefly here because I'm going to show you the graphs related to this scale. It has two components that you potentially could add up to 100 points. Half the points come from what I call the Hurricane Intensity Index. Half the points come from the Hurricane Size Index. The equation for the Hurricane Intensity Index is this. You take the wind speed in miles per hour, you divide by 200, you raise that number to the exponent 1.6, and you multiply by 50. So if a hurricane has 200 miles an hour winds, the index is 50. If the hurricane has 0 mile per hour winds, the index is 0. And it's sort of scaled that way. So this is the graph of the Hurricane Intensity Index for Michael, which are the red squares, and Dorian, which are the blue squares. 0 is when the storms made landfall in the places I'm interested in. So 0 hours would be Michael's landfall Mexico Beach. 0 hours is Dorian's landfall at the eastern end of Grand Bahama Island. That actually, in this case, just coincidentally happens to be when both storms reach their maximum intensity. So if the squares are horizontal to each other, that means they're at the same intensity. Right? And you can see both storms underwent a similar period of rapid intensification. About 12 hours prior to landfall, they're both at about the same intensity. Right? This region right there. Michael was intensifying rapidly, but Dorian intensified really rapidly right before it got to the Grand Bahama Island. Right? Now, I could have shown you wind speed, I could have shown you a Saffir-Simpson scale, that would have shown the same thing as that graph did. But size is important, and actually if you came to the presentation a few years ago, size is a better predictor of damage than intensity is in many ways. So I came up with my hurricane size index based on the radii of 64 knot, 50 knot, and 34 knot winds that the National Hurricane Center puts out as part of their forecast advisory. All right? And the way it works is, for the hurricane force winds, Sandy, they extended out about 100 nautical miles. So if a hurricane had hurricane force winds extended out 100 nautical miles in all directions, that'd be 30 points. The 50 knot winds, if they extend out 200 miles, that'd be another 10 points. And the tropical storm force wind, if they extend out 400 nautical miles, that'd be another 10 points. And that could add up to 50. Right? Now, hurricanes aren't symmetrical. The Hurricane Center provides the wind radii by quadrant, so I break that down into and divide up the points by each quadrant of the storm. You simply add up the number of points that you get out of each quadrant of the storm, and that's the hurricane size index. Right? So this is the hurricane size index, again, for Michael and Dorian, and you can see they're actually pretty close together. And there's this stretch here, 6-hour period, where the hurricane size index jumped for Michael. That's because about the time Michael became a hurricane, it just took off in terms of rapid intensification, and it got bigger at the same time. So you get that big jump in the index. And for a long time, right, Michael, the red boxes, was bigger, not significantly bigger, but bigger than Dorian was. And then right as Dorian was getting close to the Bahamas, right, it caught up in size, and you can see it, the red and the blue square are close together. Right? That's the landfall point. And so at that point, they were essentially both the same size. So to get the wind intensity size index, you just add those two numbers together. Right? And so if you do that, you get this graph here. And again, you can see the similar rapid intensification. You can see 12 hours prior to landfall right there. They were almost identical in terms of their destructive potential. At that point, Michael, the red, kept intensifying rapidly, but that was the point where Dorian intensified really rapidly and got bigger, matched the size of Michael. And so you end up with Dorian have a greater potential. Right. Now, Dorian's destructive potential is still less than Katrina. Katrina was a Cat 5 when it was over the Gulf of Mexico. It was a really big hurricane. And it had an index of 73. So the number you see here, almost 60, still isn't a record by any stretch. And both Michael and Dorian were about half the size of Hurricane Katrina, to give you a figure for that. So the question is then, well, why did these hurricanes do what they did? Right? And if you know anything about hurricanes, you know you need energy in the ocean. We usually characterize that by warm water. Right? Not much wind in the upper levels and not a lot of dry air. These are the sea surface temperatures during Hurricane Michael. Right? And remember, Michael started over here in the Northwest Caribbean, went up in the Gulf. It was pretty much over water where the temperature was warmer than 29 degrees Celsius the whole time. Right. Now this is October, so these are the anomalies. Right? So the difference from normal in the sea surface temperature. And you can see the Western Caribbean was a little warmer than normal. But if you look over there in the northern Gulf of Mexico, the water was 2 to 3 degrees Celsius above what it would normally be in early October, the northern Gulf. So that's a big reason why Hurricane Michael was able to intensify rapidly to a Category 5 hurricane before land. It was moving over water that was significantly warmer than normal for that period in October. Right? This is the 500 millibar map for those of you that know a lot about upper level maps. This is the middle troposphere. Sometimes people talk about this as being the steering level for hurricanes. And what we have here is a big ridge off the Atlantic coast. There's a trough coming in where the blue and the purple is. But the ridge basically steered Michael towards the north, and then the trough is the one that turned it northeast right about the time it got to the coast. Right. This is the heights at the 200 millibar level. Right, this is up near the jet stream level. Usually in the tropics we measure wind shear. Those of you with supercell thunderstorms, you look at wind shear down in the lower troposphere. We measure the wind shear between the 200 millibar level and the 850 millibar level. And there's this huge ridge here extending from the Yucatan over Florida. And around this ridge there were light winds. Now, that came from the NOAA reanalysis 2. This is the actual sounding from Tallahassee, Florida, on the morning that Michael made landfall a few hours later. 850 millibars is down here. You can see the winds basically out of the southeast at about 45 knots. 200 millibars up there, it's out of the south at about 35 knots. Not very much wind shear. Right, so not a lot of wind shear. We saw that with the circular cloud pattern at the top. And then the one curve here represents the temperature. The other curve represents the dew point temperature. They're really close together. There's no dry air. The sounding's moist all the way up. So the normal dry air that a hurricane would run into when it gets to the Gulf Coast, there wasn't any. So it didn't ingest any dry air. So the factors that would normally weaken a storm that got near the Gulf Coast were not present for Hurricane Michael. Right? These are the sea surface temperatures for Hurricane Dorian last year. The darker colors are the warmer temperatures. I mean, it's always warm near the Bahamas, right? I mean, how many of you like to go to the Bahamas this weekend? If you got an extra ticket, I'll go with you. Okay? And it doesn't matter whether a storm comes up from the southeast or the east. If there's no shear, if there's no dry air, that hurricane is going to intensify, and it's probably going to intensify rapidly. Okay? This is the 500 millibar map again, and this one's a little more complicated. This is actually Dorian, so that's not a steering flow, that's the hurricane. Right? One upper low here over the Yucatan Peninsula. The big feature, the important feature though, is this ridge here over the Atlantic. That blocked Hurricane Dorian, right? Remember, Dorian came east of Puerto Rico and it was going north. The ridge blocked it and turned it towards the Bahamas. And then when it got to the Bahamas, the ridge and the upper low sort of canceled each other out, and the steering winds died. So for about 24 hours, and unfortunately this is when it was over Grand Bahama Island, Dorian moved west at 1 to 2 miles an hour. And that's another thing that made the damage so catastrophic for Grand Bahama. Now eventually, this trough up here erodes this western end of the ridge, and that's what let Dorian come up toward the Carolinas later on. Here's the 200 millibar map, again that map in the upper troposphere. Big ridge here over the Gulf of Mexico and so on. Really light winds. And you can see that better here. This is the Radius-On launch from Miami, Florida, when Dorian was approaching Grand Bahama Island. 850 millibars, you can see the winds are coming out of the northeast at 10 knots. Up at 200 millibars, you're out of the east-northeast at 25. Some of that's the actual outflow from the hurricane. Very little wind shear. Now you see a little difference between the temperature and the dew point. A little drier air in the upper troposphere, not much in the lower troposphere. But you have to remember this sonde, right, being pushed southwest from Miami. So it's being pushed away from the hurricane. So let's look at one a little closer. This is the one launched from NASA Airport in the Bahamas the same time. Now, you can't really get the wind shear from this because you can see the winds coming out of the north or the west. That's actually the flow on the outer fringe of the hurricane. Right? So mainly I just want you to look here, and you can see that the temperature and the dew point are really close together. So just like with Michael, moist air all the way up, no dry air, no shear, really warm water up near 30 degrees Celsius. That's how you get a 185 mile an hour hurricane. All right, summary then. Hurricane Michael and Dorian both intensified rapidly prior to landfall. Both became Category 5 hurricanes. I hope that I've shown you that both hurricanes exhibited similar size and intensity 12 hours prior to landfall. Right. Why? Classical hurricane stuff. Very favorable environment, warm sea surface temperatures, little vertical wind shear, no drier air. For Dorian, it wasn't unusual other than the fact that we don't see many 185 mile an hour hurricanes in the Atlantic, and that's a very good thing. But the intensification of Michael was really atypical for the October Gulf of Mexico. And with that, I'll take questions. Thank you.
When Hurricane Michael developed 2 seasons ago, the tropical cyclone that came to my mind was Hurricane Opal, which was on a similar northerly track through the eastern Gulf of Mexico and made landfall on the Florida Panhandle near Eglin Air Force Base. Did you do any comparative statistics between those 2 tropical cyclones? Because Opal also went through a rapid intensification when it made landfall.
Yeah. Let me just go back to the map so I can...
And that was also an October tropical cyclone as well.
Right, yeah. I just want to refer to this. All right. So, the questions about Hurricane Opal. Opal was another hurricane that developed here in October in the Western Caribbean, moved across the Yucatan, and then became a hurricane in the southern Gulf of Mexico. And it looked like it was going to be a Category 1 storm, and it was going to come up and hit the western Florida Panhandle. And then during the middle of the night, there was sort of an upper trough to its northwest, created a favorable outflow, and in, 6-9 hours, Opal went from a 1 to a 4, but of course it was the middle of the night. So the people in Pensacola went to bed thinking they were going to deal with a Category 1 hurricane. They get up at 5 the next morning, or, well, not everybody gets up at 5 in the morning, but they get up early in the morning. And they suddenly, there were warnings out this major hurricane that was coming. Fortunately, Opal then started to weaken rapidly because of the increased wind shear. So it didn't actually hit as a 4, but everybody was out on the road. And Opal still did a lot of damage in northwest Florida, so I don't want to belittle the hurricane. I haven't been able to get the wind radii for older storms to compute my indices for stuff that far back. And one of these days when I get a couple of weeks off, I want to go crawl through NHC's archives and see if I can find stuff for older storms. So I have not done a comparison using my index. What I will say is the setup was a little different in that with Opal, it was a little more typical environment over the northern Gulf of Mexico. I mean, you did have drier air that got wrapped around in the west side. And what happened was with the trough, the environment sort of enhanced the outflow, that let the surface pressure drop really quickly, and you got that rapid spinning up from 1 to 4 on the Saffir-Simpson scale. And then, though, as it moved farther north, it's sometimes you hear people in the hurricane community talk about good trough, bad trough. Well, this was like a schizophrenic trough, right? For the first 9 hours, it was a good trough. It was promoting development. And then Opal got farther north, and then the trough was causing wind shear. It started blowing the top off Opal as it approached the coast. So in a sense, Opal was more typical of the Gulf of Mexico storm, and it was weakening as it made landfall. So a little different than the Michael scenario. There was also, if I remember right, there's a current called the loop current. It comes out of the Caribbean, it loops around in the Gulf of Mexico, and then goes past the Florida Keys and joins up with the Gulf Stream off. And every so often, a warm eddy of that will break off. And if I remember right, there was an eddy sort of in the north-central Gulf of Mexico of warmer water. And Opal, at the same time there was that favorable outflow, went over that warmer eddy. So it wasn't like the pattern that we saw here. Right? Imagine that instead of having this anomalously warm water up near the Gulf Coast, you've got this big circular ring of warmer water there. So when it went over that ring, it got a surge of energy from below. At the same time, the upper level environment became more favorable. So the environment was a little different. Opal was, and that's where I'd like to be able to calculate the size index at some point, was another smaller hurricane. So qualitatively, size-wise, it was probably similar to Michael and Dorian for that matter. Yeah?
You did a good job of talking about Dorian and its strength, but one thing I wanted to ask you about was how the steering for that storm as it reached the Bahamas, obviously it stalled out and it was horrific for the islands. Could you talk about how unprecedented that was for a storm of that strength to be caught there between two features? I mean, you see that a lot in recent years with storms that come onshore, like Harvey and Florence, that stall out as they interact with troughs and other things. But could you talk about how unusual it was for a storm that strong to get caught in that kind of pattern?
Okay, yeah, hurricanes stall, I think, more frequently than people think they do.
Sure.
A lot of times, though, it's out over the middle of the ocean. Now, you're right. I mean, first of all, I think there have only been 3 storms in the record that have winds up to 185 miles an hour. So we're talking small sample size. But yeah, the one pattern that this reminded me of was Hurricane Jeanne in 2004. Right? Jeanne was a major hurricane, right? Mm-hmm. Came up through this and looked like it was going to head out to sea. Mm-hmm. Right? And it got blocked by a very similar ridge there. And it sort of meandered out here for a number of days. And then the ridge rebuilt. And it actually pushed Jeanne almost due eastward. And Jeanne started re-intensifying again. And it got back to major hurricane status by the time it got to... But Jeanne was a weaker but larger hurricane. So you're right. Normally, if a really strong hurricane stalls, it starts to upwell cooler water from below, and then that starts to reduce the amount of energy, and it doesn't have enough energy to maintain circulation, it weakens. One thing about the Bahamas is, I mean, the warm water is deeper in the Bahamas than it is in a lot of places. That's where Andrew, turned into a Cat 5
Sure.
before it hit South Florida. It's
Absolutely.
crossing the same region. So even though Dorian stalled here, it really didn't start to weaken until a significant portion of the eye was sort of straddling Grand Bahama Island. So from that standpoint, I can't recall another example of this. I mean, the storms that I've seen stall have all been much weaker than this. So I can't, and most Cat 5 storms don't last more than, at Category 5, more than 12 to 18 hours anyway. I mean, they either run into a little more shear, because it doesn't take much to start weakening storms. So to be honest with you, I can't think of another hurricane that would match this scenario. I mean, I can think of, blocking ridges, I can think of storms that stalled and so on, but I can't think of anything like that.
Thank you.
You also see, though, storms in other parts of the ocean where that warm layer is deeper, don't if they slow down. Right? So like you had that deep warm pool over the West Pacific. Sometimes you'll get typhoons that'll slow down, and they'll be able to maintain their intensity longer than you might think as well.
Thank you so much.
You're welcome. Any other question?